Hi, everyone. Welcome to our webinar on doing computational fluid dynamics with Cradle for Formula SAE. Shiraz Butt is going to be presenting for us today. Shiraz is a recent graduate. He joined Hexagon, I think about 2 years ago as part of their early career program. His role as a technical specialist consists in supporting our customer with resolving inquiries regarding our CFD simulation software, Cradle. I'm looking forward to him telling us a little bit about Cradle, why we might want to use it for formula or similar competitions, and seeing a demo on how to actually use it for a case study with, is it a wing, Shiraz, that we'll be looking at?
It is, yeah, rear wing.
Awesome. Great. Okay, well, why don't you get into it? I look forward to hearing from you. Thanks.
Yeah, absolutely. So, hi everyone. Thank you for joining this call today. My name is Shiraz, and I'm a technical specialist in CFD within the Hexagon group. And today I'll be showing you a demonstration of a typical rear wing CAD application using Cradle. Okay, so in terms of the agenda for today, I will start by briefly introducing CFD in general and understanding why it's important and what are the typical applications. And then I will just briefly touch on the theory side of CFD, and then I will introduce our CFD solution, Cradle. And then from there, we will move to the demonstration itself, which will cover most of today's call. And I will show you a step-to-step process between the model setup, pre-processing, software post-processing. And finally, what we'll do is to change the geometry. So what we'll do is to tilt the rear wing, so changing the angle of attack, and see how the results compare against the first set of results. And then finally, share some information regarding how you can access the software if you haven't got it yet. And then finally, we'll have some room for any question and answer. And I don't know if the attendees can post any question in the comment, Alex, or?
Yes, there's a Q&A section. Yes, if you have questions, please do click on Q&A at the top of the window, and you can just enter a question where it says start a discussion.
I will be happy to answer all your questions. So I'm also joined by my colleague Sunil today, and you'll be here supporting me throughout the call. Okay, so let's get moving. So first of all, what is CFD? Why is it important? So CFD is nothing but the use of computational methods to analyze and predict fluid flow behavior. And over the years, CFD has proven to be a very powerful tool that can support engineers to design and innovate without the need to create a physical prototype. And this brings many benefits, such as cost saving and time saving as well. Another key features of CFD is that you can perform very in-depth analysis that would be very difficult to do so physically. And at the same time, you could do many different prototypes or many different testing conditions in CFD in a very fast and easy way. Okay, so some of the application you can see from the images in here. Let me open my pointer. So we have this application, which is an external aerodynamics of a typical racing cars. So this applies also to aerospace, for example, for aircraft flow analysis. And what we want to analyze from this type of analysis, what is the drag coefficient, lift coefficient, is the design of my vehicle efficient enough. And through CFD, we can perform different geometry configuration, or we could change the environment settings and see how different variables interact with the object. Another typical application is the flow distribution around buildings. And doing this physically will be almost impossible. So CFD can really help you doing that. You can import a very large number of components within our preprocessor, and you can do this sort of simulation, or you could even simulate a tsunami in this particular geometry. And then another typical application is the thermal analysis of electronic devices or even mechanical parts. And here what we want to understand is our product operating within a safe temperature, and where the main heat source is being generated. And then another possible application is, for example, the concentration of smoke coming out, for example, from a house chimney, or you could also analyzing the air ventilation within a building to find any dead zones, any recirculation zones, and from there you can improve your design to reflect that. Okay, so now we'll touch a little about on the theory side. So we start from a domain, which basically defines our boundary of our analysis model. And we divide this domain into smaller control volumes. And what we do is to solve the physical quantities by applying the governing equation of conservation mass, momentum, and energy. And from here, what we want to do is to obtain a numerical results that resolves the physical quantities. And so we have our domain divided into mesh, and we're applying all this equation to each of these meshes. And this proves to be a very accurate and results method. And this method is what is defined as the finite volume method. And it is the one Cradle is also based on. Okay, so before starting with the CFD simulation, you require some piece of information starting from the computation domain. You need to decide the size of it, whether you want it, how big or small you want it. And also you need to decide on the material properties of the fluid or the object being analyzed. So obviously different fluids will have different material properties, and can have an influence on your overall results. And another important information that you require is the type of flow you're going to analyze. Is it going to be a laminar or a turbulent flow, depending on your application? For example, if you want to conduct thermal analysis of a smartphone device, you're expecting the flow to be in the laminar zone because of buoyancy, and the flow will be diffusing towards the end of your domain. Okay, and also you need to decide on your turbulence model depending on the type of physics you're going to analyze, depending on the type of mesh you're using. There are various turbulence models that we have within Cradle you can select from. Okay, so these are some additional information regarding the domains. For example, you have your aircraft in here, and it is flying in the atmosphere, so there's no actual physical boundaries to refer from. So you need to decide on the size of that. What you want to make sure is that your flow is appropriately captured, especially on around the aircraft. So on the sides, you're expecting to have some vortexes, and on the rear of the aircraft, you're expecting to have some wake. So you want to make sure your domain captures this area. And to do so, we have some numbers that are typically used. For example, if we take our aircraft and we call this length as L, we want to apply at least a 5 to 10 length size towards the end of your domain to make sure that all the flow is captured on this side, and then at least 3 to 4 lengths on the sides, and then 2 to 3 lengths, I would say, at the inlet, because we are assuming the flow to be nice and uniform, and we want to make sure the same is also applied to the outlet of the domain. Okay, so now I'll just briefly introduce our CFD solution, which is Cradle CFD. And Cradle started as a Japanese software in 1994. And over the years, it developed its CFD code to the point it gained significant market share in the Japanese market. And it also expanded in the Americas and European region later on. So as a key milestone in the, let's say, business side, in 2016, Cradle was acquired by MSC Software, and a year later, MSC Software itself was acquired by Hexagon, and we are currently still part of Hexagon. And if you look at all these milestones, these are related to the code development. So starting from a Cartesian mesh type solver, we move into integrating more and more advanced feature. Okay, and one of the key features of Cradle, so we can attribute this to a typical Japanese katana. I don't know if you're familiar with this, but some of the properties of this item is they're very sharp and easy to use and robust item. And these characteristics can be applied to Cradle as well. It's a simple to use software with a easy interface, and the meshing as well is very fast, and it has a very robust solver to help you solve even complex physics. So within Cradle, we have, so we start by importing our geometry normally, and you can use your tool of choice. Cradle can support most of the CAD extensions. And then we have two separate modules. We have the SS3 module and the scFLOW. The SS3 makes use of a structured Cartesian mesh. And the priority is to create a fast and simple to use simulation. And the typical applications include electronics and architecture and civil engineering. And overall, SSTream is a very excellent product if you're dealing with a model with hundreds or even thousands of different parts. And on the other side, we have scFLOW, which can be considered our general purpose CFD tool. And it is based on unstructured polyhedral mesh. And this is where the shape geometry is very accurately captured. And this is why the applications include automotive, aerospace, if you want to analyze what is happening on the surface of your object analyzed. And then both SSTream and scFLOW modules, they share a common post-processing tool called scPost. And here, this is where you can create some animation, some contours, and any data that are needed for your reporting. So let's discuss on the outline of scFLOW. So this is the software we'll be using for today's webinar, since obviously our wing geometry is a slightly complex and curved shape. So we want to very accurately capture this geometry. So we normally, as mentioned earlier, start from a CAD geometry, and you can import any CAD format. And what we do in the preprocessor, we apply our, we create our analysis model, we apply the material properties, we register the surface that are needed for our model, and we create the mesh. And then as an output of this preprocessor stage, we have our PPH file, which is called project file, which contains all the information I mentioned earlier. And then from the preprocessor, we also extract two separate files. One is the GPH file, which is the mesh file, and the SPH file, which is our analysis condition. The SPH file is nothing but a test file, which contains all the data that are needed for our solver. So these two files are imported into our solver, and this executes the analysis, and it provides two set of results. One is in numerical form, which is called the L file or log file. Another set of results is our field file. These are needed for our post-processing. So finally, on the post-processing, you import the FPH file, and then you can create your animations and etc. Okay, so now moving on to the demonstration side, you can see from this image, this is a typical SAE Formula vehicle, and the rear wing constitutes a quite major part of this vehicle, alongside the obviously tires, the front wing, chassis, and power plant. And as you may know, the purpose of the rear wing is to generate downforce, and this provides improvements when it comes to the vehicle stability, especially during cornering and braking side. And for our model, we'll be using a two-stage rear wing based on a NACA 6412 profile. And as you may know, when you increase the stages, what happens is your primary wing generates most of the downforce, and the secondary wing helps to energize the flow and also to delay the flow separation. Okay, so the aim of today's demonstration is to show you how easy it is to set a typical simulation using scFLOW. Okay, so in terms of the outline of the model, I mentioned we have our two stages wing based on the NACA 6412 profile, and we'll be setting an inlet velocity 30 meters per second, and at the outlet we'll be assuming that the flow is nice and smooth, so we apply a 0 Pascal static pressure outflow. And in terms of the domain, I mentioned earlier we want to make sure the flow around the wing is well captured, and this is why I set up this number. So L being my characteristic length of my wing, I applied 1.5 length on up front, 1.5 on the sides, and 4 lengths on the towards the outlets. Now this number can be increased depending on the type of simulation you're doing. For example, if your geometry is large and your velocity are far higher, you might need to play with these numbers. But the overall goal is to obviously capture the flow as accurately as possible. Okay, and in terms of fluid, we are dealing with air, and our wing is modeled as a obstacle, so there's no material properties applied to the wing. Okay, and in terms of simulation type, we'll be performing a steady state analysis with 1000 cycles. This is just for the safe side. I'm expecting the simulation to complete much earlier, and the environment condition are default temperature 20 degrees, and we'll be using a SST K omega turbulence model. In terms of the wall boundaries, so we assuming the boundary of the domain are not affecting the flow, and this is why we applied the free slip condition. Okay, so from here I'll be moving to the demonstration as well. So we start by launching our CFD software, and as I mentioned earlier, we have the scFLOW and scStream module, and within each module we have the preprocessor, solver, and post-processor tool. And within this, what we call a kicker, there's a user guide. This is a very useful tool, especially at the beginning if you want to familiarize with the software. And within the user guide, we have plenty of exercises you can refer to, both in the operation and exercise manual. Okay, so we'll start by launching my preprocessor, and that will take a couple of seconds to launch. And what we'll be doing is to upload the geometry in here. So we can start by naming the project. So I'll say a test, for example, and I'm going to save it here. I'm going to save on my desktop actually. So let's create a new folder, SAE test. I'm going to select this folder, and once I'm happy, I'm going to create it. So the first thing we do is to import the geometry. As I mentioned earlier, we can import any geometry formats. So in this case, I'm going to upload a XT format. So there's two ways of doing this. You can either import it from here, or you could just simply drag and drop the file into the preprocessor window. So I'm going to do so now. So this is my file. I'm going to just drop it here anywhere. And there you go, it's been uploaded very immediately onto our preprocessor. Okay, so from here, what we'll do is to, first of all, create the domain. And to do so, we're going to select the create parts command here on the top left-hand side of the navigation bar. And here we're going to select a cuboid, and I'm going to rename it as domain. And since I don't have any reference about the measurements, what I will do is to create a domain around this object. So what I'll do is to either can right click and hit select all parts, And you can see you could also do from the navigation tree in here. And then I'm going to select this option here, calculate size on selected part, and all the variables already, all the numbers already populating here. So for example, if we do a preview, you can see there's already a tiny domain built around this object. But obviously what we want to do is to extend this domain size. And we can do so from this command here. And we have our X and Y, Z coordinates. So let's start by on the Y coordinates. So now my Y size is 0.6. So I can apply Y min axis of, for example, 1.2. So this will be 2 times the initial length. This is slightly bigger than what I mentioned earlier, but we can use these numbers. And on the outlet, I'll be applying 4 times these values. So that would be 2.4. And then you can always preview it and to see if the values are correct. And then we'll do the same on the z-axis and x-axis. I'll be applying a factor of 1.2 as in here. Go from the minimum maximum, 1.2 here, 1.2 here again. And I can preview it. You can see. So I think the domain is quite big enough to for our purpose. We might want to extend from the results. If we see the flow in novel capture, we could always extend this further down. Okay, and also I'm going to register this cuboid as a fluid region, and this will be creating here. So now from here, we imported the geometry, and if there's any modification that you want to do, you can do from here. There's very option to play with your CAD geometry within the preprocessor. And then from here, what we'll do is to apply the material properties. So here you can see the list of all the parts in here. I will start by selecting the domain and apply the fluid attributes since we are dealing with air. And I'm going to expand my incompressible gas list and apply here. So this will be populating here, and everything else I'm just leaving an obstacle for today. If you were to do, for example, a thermal analysis, you will need to obviously apply the material properties if you're interested to see how the temperature evolves within your object. But this is not the case today. We're just dealing with external aerodynamics. Okay, so once you apply your material properties, you will see also the error message will disappear from here. And then what we'll do next is to apply the boundary conditions from this window. And we'll start from the analysis type. We have the flow chart, and if we select it, for example, this will enable the thermal equations. In terms of methods, I'll be using the default standard SSTK omega turbulence model, which is, I think, okay for this type of simulations. And I'll proceed into the basic settings. So here we select between steady state and transit simulation. For now, we just do a steady state analysis. I'm going to increase the cycle numbers to be on the safe side to 1000. And we can proceed further down. There's no initial condition that we want to apply, so we'll be moving directly into the flow boundaries. Before that, there's an important step we need to do. As you can see here, there's nothing showing up, so what we need to do is to register the surfaces of the inlet and outlet. So once we have that, we can apply our boundary condition. So let's move to the register region tab. And I'm going to select with my mouse simply. Just want to make sure we have the face selected in here. I'm going to click my inlet. I'm going to rename it and register it. This will be populated here, and do the same for the outlet and then the walls. So I'm going to select all 4 boundaries on the sides and I'm going to call this wall. And then also what we want to do is to register the surface of the wing. Now, why is the registration important? One is to apply the boundary condition, and then secondly to apply any mesh refinement, and it will be the case in this model since we'll be applying some refinement on the wing surfaces. And then finally also in the post-processing tool you can extract some images, some animation based on your surface registration. Okay, so I will only have the wing left. So you can see we have the domain on top, which is enclosing the wing. So I'm going to uncheck it from here. And now I can access the surfaces on the wing. So I'm going to select the upper and lower section. I'm going to call this wing 1. And then I'm going to do the same for the upper wing, selecting the surfaces and calling this wing 2. And also I'm going to register the M plates for mesh refinement. So do 1 and 2 and call them M plates. Okay, so I think we are done for the registration side. I'm going to show back the domain. And if you go back to the condition and into the flow boundary, now you're able to see all the surfaces registered. So I'm going to apply a boundary condition at the inlet. So we select the surface, click the inflow and outflow condition, and I'm going to apply normal velocity at 30 meters per second. So you always pay attention to the units. Sometimes we compare our data with for example, data online, and we might confuse the units. So it's important to make sure we're using SAE units in here. And we're going to leave everything else as default. And I'm going to set this boundary. I'm going to do the same for the outlet. In this case, I'm going to apply the static pressure outflow of 0 Pascal. And in terms of flow boundary, I think this should be all. So we can move on to the wall boundaries. And I'm going to select my wall surface and check the wall boundary. I'm going to apply free slip conditioning here. And this is set. Okay, so in terms of boundary condition, I think this should be all. And now we can move into the analysis control setting. So this is where we can change our, for example, our matrix solver parameters or our convergence criteria. So this comes in a little bit more advanced stage. So an important step that we'll do today is the output of list file. So we want to extract the forces information of the wing, and we can do so from the list file, which is the log file I mentioned earlier, the numerical report that we obtained from the solver. So from here, I'm going to go into the output surface force, and I'm going to create a new condition. And here I'm going to check my wing 1 and wing 2 and make sure that all the forces are being output, and I'm going to select OK. So this will be shown in here. And in the output of field file, you can change how often you want to extract your field information. In this case, you're only interested on the steady state results, so we will wait until the last cycles. Okay, and finally, you can change the file naming here. For example, we already name our project, so all the related file will be named the same, but you can always change in here and hit apply. Okay, so now we've done the surface registration, we've done the material properties and apply the boundary conditions. And the next step will be building the analysis model. So this is where our CAD geometry is being analyzed, and it checks for any interferences and basically divides our analysis model into tiny triangles. So once I'm happy, I can create the facet. And you can see here, there's no issue in our model, so we can proceed into building analysis model. So once this is done, your model will change from the initial green color to the blue color you can see here. Okay, so once we built an analysis model, we can proceed into the meshing stage. So in scFLOW, meshing is done in 2 steps. First, we create the arc tree, and then we apply the meshing layer. So with the octree, we basically represents the building block of our mesh, and it is used for the resolution of our mesh. Okay, so I'm going to start by opening the octree parameter dialog, and there's various settings you can play with. You can, for example, input a target number of elements. For example, here 100,000. It's a number that you can use for this type of model. What we're going to do is to apply the parameters in detail. So I'm going to select in here. And what I'm going to do is to restrict the minimum and maximum sizes of the octree to make sure we don't have very coarse elements in here. So I'm going to apply minimum maximum of 0.1. And then what we'll do is to move to the second tab in here to apply the refinement on my wing surfaces. So you see here, these are the surface we registered earlier. So we have our wing 1 and wing 2. So I'm going to apply the refinement. So we start from the basic settings, and we want to apply a refinement level in the order of 2. So the next level will be 0.05 and then 0.025 and so on. So I'm going to apply a refinement of 0.0125. And the influence range is basically tells about the propagation, how many layers you want to propagate externally. You can see from here. So this will be 3 by default. So you have your refinement in here, then you have one layer in here and second one and so on. So I'm going to apply influence range of 2. And then I'm going to refine my end plates as well. We're not so interested in this analysis, so I'm going to keep a little bit coarser. And okay, so in terms of refinement, we should be okay. And once we do this, we can create our octree, and you'll see within seconds the octree is generated. So this is a resolution of what the mesh will look like once you apply the prism layers. And to see our refinement on the wing, we can check the cross section from the view window cross section, and we can see the YZ plane to make sure. Going to see the opposite side, and you can see we have some 3 level of refinements. So this should be good enough for our model. Okay, so from here, once we've done the octree, we can proceed into the mesh parameter. But before doing that, there's a quick tip that I want to give you. So as you may be aware, so the flow at the outlet of the wing will be severely disturbed. And what we want to make sure is to capture this, what is called the wake region very accurately. So at the moment, all the refinement we did was on the wing itself, but we don't have any refinement on this region. So what we can do is to register a volume region around the wing, and we can refine that one. So let me show you quickly how we can do this. So if you go back into the register region stage, and earlier we did the registration of the surfaces. So I'm going to select the volume region, and under target, I'm going to select numerical region and then press new. Okay. And then I'm going to call this numerical region. And we want this to be a cuboid. And what we can do, as we did when we created the domain, we can select our wing and create around it. So I'm going to do this. So I'm going to uncheck the domain and right click and selecting all the parts, and then calculate the size from there. And if we do preview, you can see there's a smaller numerical region created. So I'm going to check back the domain just as a reference, because we don't want this region to be the same size of the domain. So I'm going to extend this region a little bit. So starting from the Y direction, I'm going to apply a value of 0.1 and 0.4. Let's see how big this stands. Okay, so I think we should be fine. We can extend a little bit to be on the safe side. And then we going to do the same on the z-axis and x-axis. So once we've done this, and you can see now we can refine this region accurately to capture the wake on towards the outlet of the wing. So I'm happy with this and going to close it. So we will have to redo the octave again, just on the refine. We need to apply the refinement on my numerical region, and I'm going to input a value of 0.025 and again influence a range of 2. This is not necessary, but it helps to propagate your mesh nice and smoothly. And then I'm going to recreate this again, and we can check our cross section to make sure the refinement is as expected. Opposite side, now you can see here there's a whole region around the wing, which is well refined. Okay, so once we're happy with this, we proceed into the mesh parameter. So this is where we insert the prism layer, and by default we have a value of 0.2 and 2 number of layers, which is I think fine for our application. Normally we tend to apply a greater number of layers to capture the flow on the surface. Normally apply like around 5 to 10 layers to capture this accurately. I think we are happy with this. So I'm going to create the mesh. So this process will take a little bit more time. It can take maybe a couple of minutes or 5 minutes, depending on your type of machine you're using. So I'm going to switch to a model that already has the mesh created. And I'll leave this in the background. So this is, you see the prism layer have been inserted in our model. You can check again our cross section. And same plane. And here you can see the layers have been inserted, and there's 2 layers on the edge of our airfoil. Okay, so once we're happy with this, we move into the final stage of our preprocessor side. We execute our our model, and from here what we start is the mesh file and the analysis condition file, the SPH file that I mentioned earlier. So once we do this and click OK, we will have these 2 files, and as well the project file will be also saved in the work folder. Okay, so now I'll be moving into the solver side. So from the kicker, I'll be open the solver. So this is solver window. So this is where we will be registering our job, and this is where the simulation progression will be shown in terms of graphs. So in order to upload your model, you can either hit file open, or you could just simply drag and drop your SPH file into here. So I'm going to show you that. There's my SPH file. It is being uploaded here. And you can see the information regarding the number of cycles. And as you start your simulation, it will give you an estimate of the ending time. Okay, so once you start this, what will happen? Your simulation will start with progress starting from cycle number 0 up to 1000 cycles. And if the convergence occurs earlier, your simulation will stop before that, and it will give you the output of the log file and the FPH file. So I'm going to show you directly the end of this file, because the simulation time, it took me around 15 minutes for this model, and that also depends on the type of machine you're using. So I'm going to upload the final stage. So I'm going to replace this file, and you can see here. So this is the converger status, and basically what it's telling you, it's checking all the variables, all the residuals, and as soon as they reach the converger criteria of -4, so this is logarithmic scale, the simulation will stop. You can see here this convergence has been reached only after 424 cycles. And so this is the convergence status. And also you want to make sure that your mass flux is close to 0 because you want due to conservation of mass. And also you want to make sure that your other variables are nice and smooth. Sometimes what happens is your simulation stops if we reach convergence but your variables are still not stable. In that case, what happens is you might need to increase your number of cycles, or you might need to play with your mesh, etc. So our forces are nice and smooth, and so we are happy with our simulation. Same for the turbulent variables and the pressure as well and velocities. So this is the status of our analysis condition. And what you can see here on the top is a log file launcher. So this is what I'll be showing you next. So I'm going to open the Kicker and just drag and drop the L file into this icon here, which is the L file launcher. And a couple of seconds, it should be uploading the L file data. Okay, so that's in here. So what you can see here, it's a numerical summary of all the simulation that's happened. So all the graph you were looking earlier, they are also found in here. And we can see we can jump between cycles and we can check, for example, our boundary flow rate at the inlet. So if you press in any number, there will be a graph generated accordingly. And so this is what happens. So if you remember earlier, we asked the preprocessor to export the information of the force acting on the surfaces, and we can find them in here. We have our register region, wing 1, wing 2, and we have the total of the forces. So in this case, if you remember from the axis, our drag is in the y-axis, and the lift will be in the z-axis. So we can find the force information in here. You can also plot the graph. Obviously, these values are not quite meaningful since we only do a steady state analysis. And once you know this information, and you can evaluate the lift coefficient and the drag coefficient by simply dividing this value to the dynamic part. So 0.5, the density and velocity square. Okay, and then also what you want to check, you have information regarding the y plus and the number of elements. In this case, most of the elements are in the log row region, which is expected for this type of simulation. And additionally, you have also a steady state check in here. So these are all the residual. And if you see a number 1 in the brackets, it means the convergence has been reached. Okay, so from the L file, I'll be moving on to the post processor. So I'm going to, from the Kicker again, I'm going to drag and drop my FPH file onto here. So this will be uploading our post processor tool. So this will be showing here in a second. So we have our model in here. There's a plane already registered, and the surface is registered as well. So we start by creating a plane object on the cross section of this wing. So we're just going to change the orientation. Since it is currently perpendicular to the z-axis, we want to be perpendicular to the x-axis. So you can see here there's a plane being created, and I'm going to hide the surface object for the time being. And I'm going to move the orientation to see the cross section more accurately. And here we start by creating some contours. So we can start on the plane object. We have the contour option, and then we can display, for example, the pressure. And here you can see some values in here. We have, as expected, lower pressure on the lower side of the wing and higher pressure on top. And this is creating a net downforce. And we can also plot the, for example, the velocity. And you can see here there is a wake region on the towards the outlet of the wing, and this is why we did the refinement earlier with the numerical region to capture this area more accurately. Okay, and additionally, we could also create some vectors. So I'm going to uncheck this for the moment, and still in the plane object, we can do a vector analysis. I'm going to press display, and we can display the velocity here. And you can play with the numbers to make it a little bit more nicer. And also there's a way option to create an animation as well. So you can export all this data. You can there's a camera object here where you can create an animation in the MP4 format, or you can just simply take a screenshot with high quality for your reporting. Okay, so once we know this, so I'm going to show you how you can modify the geometry and change the angle of attack of the upper wing, for example, and then see how the results compare. So I'm going to close this for the moment, and I'm going to open my original model. Okay, so we have the modeling here, and what we'll be doing is to perform slight CAD alteration. So first of all, I will return to prepare parts. If you're using the same geometry, you could just recreate a new file by import the geometry as I showed you earlier and perform the steps again. So this will be a little bit quicker. So I'm going to uncheck the domain for now, and I'm going to press the modify parts command, and then select the transform tab in here. And then I'm going to select my upper wing here and select rotate. And I'm going to rotate based on the x-axis. So I'm going to select 1 in here. And I'm going to apply an angle, for example, let's say 10 degrees. And we can preview this and overlay to see how this varies. Okay, so I think we're happy with this. So once we've done this modification, we will need to create the to recreate the analysis model again and to recreate the octree and mesh again, because obviously we changed the geometry. There is a way to avoid all of this, and is, for example, you can change the inlet velocity to reflect the angle of attack. So under the conditions, flow boundary, instead of applying a normal velocity, you can apply some velocity components in the x, y, and z axis, and you can do so to reflect the angle of attack. And the key benefit of this step is obviously you don't need to redo the meshing and the octree generation. And this is very useful, for example, if you're doing a study of different angular attacks, and this methods will be much quicker. And another difference will be when you calculate your lift and drag coefficient, you will need to change your formula according to the angle. Okay, so I'm going to skip the octree and mesh generation step since I showed you earlier, and I'm going to pull up my slides and show you the results of these changes. So we already discussed about all the steps in here: registering surface, creating the octree, material properties, mesh generation, and then the solver settings, and then the alpha in here, as showed earlier from the forces on the alpha, you can extract the lift and drag coefficient, and you can plot them on a graph. You can extract this information on a CSV format, and you can create plots on Excel, for example. And then, so this is the results from the first set of simulation. You can see the pressure coefficient distribution. We don't have the CP value by default, so you will need to register this, and I will show you this in a moment how you can do this. And now you can extract this graph. And again, these are some contours that are generated on the post processor. And then there's an animation like I showed earlier, and the pressure control on the weak surface, as mentioned earlier, high pressure on the upper side and lower on the lower side generating net downforce. And then the geometry changes like I showed you earlier. And then before going to the post-processor, I think a quick way to understand or to check the simulation results is by checking the ELF file. So previously, we obtained these force values, and by changing our angular type, we have some slight increase in force in the y-axis, which is our drag in this case, and slight decrease in the wing. So from this simulation, what happened is our performance has slightly degraded of our wing performance. And you can also see from these plots in here of the pressure coefficient value. You can see from towards the leading edge, trailing edge of the wing, there's a increase in pressure, and this is causing less downforce. And even on the leading edge, we have a slightly higher pressure compared to the previous case. And this can be shown also on this plots in here. So I'm going to quickly show you how you can create this CP graph. And let me open the FPH file again. In order to do this, we will first need to register the CP value, the CP variable. And you can do this from the object in here. If we double click it, we have the variable registration command. And for the CP variable, the equation will be pressure divided by 0.5 times our density. I'm going to use this value times our velocity square. I'm going to show you using SAE units. I'm going to call this CP, and we can register our variable. And you should receive a confirmation message in the window. So once we've done this, we can go back to the plane object. I'm going to hide the surface for the moment, and we can plot the CP graph. So on the plane, we have our mesh command here, and there's a slash in here called graph. And we're going to select our variable of interest. In this case is CP. And if we click on the object, we can see there's a graph generated. Now currently the start and ending points are not correct, so I'm going to move this graph from the main window, and then I'm going to select the plane again so we can move these points to the desired location. Okay, so we can zoom a little bit more, and also we want to make sure that our graph is showing the correct axis. So in this case, we're not going for the length, but because it will be showing the entire length. So I'm going to set the y-axis only. And here you can see we have the same plot that I showed you earlier. And you can extract this plot in as a data. You can do so from the save command. You can name your file and save as a CSV format. Okay, so now going back into the results session. So I've showed you overall how you can set up the model in scFLOW, and you started by importing geometry, applying the various conditions, and you essentially start the solver and upload your list file or your FPH file into post-processor for reporting. And we see by changing our angular tag, our performance has slightly changed on the negative side. And obviously you can change your angular tag even more to see at what point your flow stalls, and you can do various simulations. As I mentioned earlier, the quickest way will be rather than changing the geometry itself will be to change the inflow direction to reflect the angle of attack. Now, just a few considerations before you jump into the conclusion of your results. it is always worth having a sanity check. And by starting to look into your analysis model, you want to make sure it is accurate enough. It wasn't the case in here, but if you were to analyze an object which is much smaller than your domain, you will need to play with your faceting settings to capture the geometry accurately. And also you want to make sure your octree and mesh is accurate to capture the flow details. And you can do this by creating, for example, numerical regions or refining geometry at some given surfaces. And you could add some prism layer to, for example, capture the boundary layer if you're interested. And as mentioned earlier, when it comes to the condition, by default, SAE convergence once it reaches a convergence criteria of -4, but you might have to make these settings a little bit more stricter. And you can do so from the analysis control setting in the preprocessor. And in this case, we were able to obtain very stable results at the end of our convergence, so we were happy with those. And finally, obviously, you might need to change your turbulence model according to your physics analyze and type of mesh. Okay, so in terms of demonstration, I think this should be all from my side. Alex, you can take over and just give a brief on this.
Yes, for sure. So I shared the links that you see on this slide right in the chat. And if you're watching this on YouTube, then those links will be in the description. So either way, you'll have an easy way to get at these things. I should emphasize that the student competition bundle and the student editions are both free. There is an application process for the competition bundle for teams to demonstrate that you really are a team with university. The process for getting the student editions is a little bit easier, but those are of limited model size. I would say if you just want to get into something, the fastest way to do it is with the student edition. But if you're serious about using the software for a competition, you can do that for free, and it's worth applying for the student competition bundle. Like Shiraz says, we have a number of upcoming webinars. The next 3 are going to be a series on Adam's car, and they're going to have a cumulative series of new concepts for you to pick up. And I encourage you to follow us on social media to be able to keep up with the rest of this series. Shiraz, thank you for the very helpful webinar. I think that we're ready for Q&A.
Yeah, absolutely. Don't know if there's
Actually,
any questions.
I've got one to start with that somebody had asked on Reddit when I had posted about this webinar there. They wanted to know, how does Cradle compare to other common software for CFD? Why might they really want to use Cradle, especially for Formula SAE?
Yeah, absolutely. So when I mentioned earlier, the setup of the simulation is very straightforward, and the geometry import, the way we set up the surface registration and we apply the meshing is very straightforward. And we also have a lot of material available in our website where you can refer to. But overall, even from my own experience when using other competitor products, the way it is laid out is very simple to use, especially for new users. And at the same time, we also have a lot of detail commands for more in-depth analysis for more, let's say, experienced users.
Yeah, that all checks out with me. I find that when I have students and professors try Cradle, they tend to just pick it up pretty easily. One of my favorite things about it is that it includes a lot of really helpful tutorials and documentation. So you can just download Cradle and the corresponding documentation onto your machine, and you can work through a few basic exercises, and then from there you can pick up a number of other skills based on topics that you're interested in. I would say start with the operation manual to figure out the basics, and then the exercise manual will take you to whatever it is that you really want to focus on.
Yeah, absolutely. So when it comes to the operation manual, we have 3 initial tutorials, one covering thermal analysis, one covering external aerodynamics of aircraft. So it's a good starting point, and then obviously you can switch to more complex examples in the exercise manual. And another point I want to mention quickly, we have recently launched our Nexus community forum, and that is specially designed for students where you can post your questions, and myself and my colleagues will be happy to help you out. I'm not sure, Alex, if you have the link to hand for
I can
Cradle
pull that up.
community. Yeah, that would be great.
Can I ask you another question?
Yep, sure, go ahead.
So we were talking about how long the domain has to be able to capture the flow profile, but how about how wide or how tall relative to the size of what you're analyzing, the car or the wing?
Yeah, absolutely. So first of all, you may have an estimation where your flow is going to be more affected. And for example, on the rear side, you know that the flow will be quite on the turbulent side, but the same could apply on the rear side and on the top and bottom. So you want to extend your domain to contain this, this flow behavior. But at the same time, you don't want to create a very huge domain because that will affect your mesh size and overall your simulation time. So we have some, I did share some numbers earlier. So for example, if you have your characteristic length, you can increase it by 2 or 3 lengths if you're dealing with a certain aerodynamics, or if you're just doing a normal for natural convection, you can reduce these numbers to reflect that. Okay, thanks for sharing the community link. And this is for everyone to access. I don't think there's any registration needed. The only time you need to register if you want to post a question. If you want just to follow for any updates, you can do so freely.
I see a couple of questions from somebody who wanted to know what are the system requirements for Cradle, and I looked that up. I just want to call out my answer. You will need Windows 10 or Windows 11. If you're dealing with Windows, the requirements are a little different for Linux, and you'll want a 64-bit processor. In general, Cradle can be pretty flexible on some of the other system requirements. It depends on things like your model size, but you would want at least 8 gigabytes of memory, and you'll need about 10 gigabytes on your hard drive just to install Cradle. And your graphics card should support OpenGL. There was also a question about the maximum cell count on the student version. You can do 1 million elements, which seems pretty generous to me. What do you think, Shiraz?
Yeah, absolutely. I think with our model show earlier, we were in the range of 100K or 200K. So absolutely, you'll be able to mesh this type of scenarios quite easily. Okay, I can see a question from Alex regarding the tight gap elements. So normally we want to obviously capture this area as accurately as possible. So we normally recommend applying at least 5 to 10 elements in this region to obviously capture what is the flow within the gap. So there will be a lot of changes happening there. So applying a decent number of elements is necessary.
Yeah, I think we're set. I have one last question.
Yep.
So I had mentioned the built-in operation and exercise manuals for Cradle scFLOW. Do you have any other suggestions on where people can go to learn more about Cradle?
Yep, absolutely. So I mentioned earlier about Nexus community. We also have Nexus Academy, which is our new portal that we launch. And over there, you can find a lot of tutorials, a lot of webinars like today's one, where you can see different related videos, and you can use them as a reference to to gain some to familiarize yourself with the software. So Nexus Academy will be the place to look into.
Sounds great. Shiraz, I think that we're about set.
Great. So yeah, thanks everyone for joining today. And thank you, Alex, for helping me out.
And you did the hard work. Thanks for preparing such a helpful presentation. I think that people will be able to download Cradle, install it, follow along, and then apply it to their own designs, which is really exciting.
Great. So yeah, for any follow-up questions, please use the Nexus community page. And for any question related to today's webinar or for anything else, please post the question in the community.
Great. Thanks, everyone. Have a great day.
Okay. Thank you. Bye-bye.